Welcome. We're now going to have a look at transformers. So before we start, let's work out what is actually a transformer. So a transformer is an electronic device made up of two coils. So we have a primary coil, we're going to call it the primary coil, and it's got a symbol of 1 little 0 there. And this is going to be attached to an AC power source. So this power source alternates the current forward and backward as an AC device. And in our demonstration yesterday, we used 2 volt and it was 50 hertz. In other words, this current reverses itself backwards and forwards 50 times per second in that coil. And close by, we had a secondary coil. When I say close by, this secondary coil, which is 20 and is secondary, this coil was attached to a voltmeter. Now, a voltmeter in this coil here is going to be inducing a EMF, which is going to be induced 50 times per second. So our voltmeter had to be a special voltmeter called a CRO, which is a cathode ray oscilloscope. Cathode ray oscilloscope. Now, that cathode ray oscilloscope was able to measure a voltage by making it into a graph on a screen, and this measured the EMF that was generated in the secondary coil every second. So what's actually happening here? So we go forward a bit. So here is our primary coil one more time. And we want the energy of the primary coil to be transferred into this secondary coil. This is the electrical energy from the primary coil into the secondary coil. Now, we are making one assumption here, that no energy is lost in this transfer from one point to another. This is the ideal situation. So this is the ideal transformer. Okay? And an ideal transformer assumes that the energy of the primary coil is equal to the energy in the secondary coil. We're going to set up that the primary coil has N windings, so N with a little p, and the secondary coil has, that's not capital S, N with a little s windings. So let's just take our primary coil here and just give it some nice numbers so that we can work with. So how about we say NP in this case is 10 and NS is equal to 5. So there's twice as many in the primary or the first coil than the second coil. And don't forget, the primary coil is attached to the AC voltage. Okay, and let's go from let's make a nice value 20 volts there. Okay. Now, if all the energy from the primary coil is transferred to the secondary coil, that means the power in the primary coil, must equal the power in the secondary coil. Now, why is that the case? Well, power, as you know, is energy divided by time. It's measured in watts or joules per second, and therefore, if the time unit on both sides of the primary and the secondary coil is the same, so say for instance per 1 second, then the primary and the secondary powers must be the same. That is, once again, if no energy is lost. We also know for electrical energy, power is equal to voltage times current. So going back, we have the voltage in the, sorry, I've just got to move this up because I've got that in the road. So I'm just going to, I'll just do it down here. Voltage in the primary coil times the current in the primary coil must equal the voltage in the secondary coil multiplied by the current in the secondary coil. So if we are inducing EMF into the secondary coil, so EMF is going to be induced in here, into the secondary coil. This EMF comes about because the change of flux, the phi beta T, from the primary coil induces a change of flux, I'll say that again. The change of flux in the primary coil is the rate of change of the flux in the secondary coil. I will say that one more time so there's no confusion. Because these coils are close by, the rate of change, the change of flux from the primary coil is the same as the flux in the secondary coil. Because this coil over here is in vicinity of this flux here. So the change of flux from the primary is the change of flux in the secondary, and that induces EMF. So that means that the voltage in the secondary coil will be not created, but transformed from the EMF in the primary coil. So going back one more time to our situation, here's our primary coil, okay? And we said that this had 10 windings and it was 20 volts AC. And our secondary coil here had 5 windings. Because the EMF induced is minus N divided by T, the EMF in the secondary coil will only be half the voltage of the primary coil because the number of windings influences the amount of EMF. In a 10 winding coil, we have 20. So what would we have in a secondary coil? So the V in this one here is 20. The V in this one, so the voltage of the primary is 20 volts. The voltage in the secondary would be half that. That would be 10 volts. Okay. Now that means that this is going to be what we call a step-down transformer. What that means, a step down reduces voltage from the primary to secondary. The step down refers to only the voltage. So from the original coil, this is the primary coil, down to the secondary coil, we have a halving. But going down to the power in the secondary coil the power in the primary coil must equal the power in the secondary coil. So how does this happen? If the power here must equal the power here, then we remember that this is IP here and IS. So this number multiplied by this number must equal this number. So if I decrease the voltage in this one, I must increase the current in that one. So let's give ourselves some numbers. So if we say the power in this coil here was 100 watts. So remembering that P equals VI, so V times I would equal 100 watts. So we wouldn't be able to work out that that's 5 amps. So 20 times 5 is 100. So in this coil, we have 20 volts, and I've just told you randomly that this was a 100-watt coil, so this has got 5 amps in it. Remember, that's AC, it's moving backwards and forwards. Now, going over to our secondary coil, if the power of the primary coil equals the power of the secondary coil, so there's 100 watts in our secondary coil. So this has still got 100 watts in it. So there's no power loss. There's 100 watts here and 100 watts there. That means that this number, that's the 10 volts, multiplied by this number here, must equal 100 watts. If that is the case, then this must be 10 amps. Did you notice what happened? In a step-down transformer, in this one here, we multiplied by a half. Here, when the voltage went down, the current went up, and we multiplied by 2, the reciprocal. So that means that we're not making energy out of nothing. Our trade-off here, as we step down the voltage, the current stepped up. Let's try another example with a little bit less all the numbers all over the place. So here's our primary coil, and let's make ourselves have 50 volts in there. Once again, it must be AC. And I'm telling you that there will be this power in this coil here is 250 watts. In our secondary coil over here, we want to know what is the voltage in there and what is the current. Okay, so let's have a look. I'm going to give you the number of windings, so let's just do a nice windings number. So let's make this n equals 20 and this be n equals, let's make it 2 windings. I know there's more than 2 in that diagram, but let's just make it nice. So this is our primary coil and this is our secondary coil. And I like drawing these little diagrams with the little squiggles beside because it makes it easier, and you can use the NVIP under each of these. N equals VIP, very important person, just like me. Okay, and the number of windings is 20, that is 2. Filling in the rest of what we know, now this is the, we often put little letters and so on. This is NP, VP, IP, and PP. And that's S, 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 and S for secondary. I know that this voltage here is 50 volts, and that power is 250. So what can I fill in? I can fill in this value here because I know that V times I, power is equal to V times I, would equal 50 watts. So that must be 50 amps. Okay, so that times that equals, sorry, 5 amps, not 50 amps, 5 amps. I'll just see if I can get rid of that. Therefore, 5 amps. Good. Right, now, let's have a look at what type of transformer we've got. We're looking at the ratio of the loops. This will be a step down. It's a divides by 10. Okay, so this means it steps down the voltage by 10. So this would be a divides by 10. Remember, step down transformer, we're going to talk about step up in a few more moments. It's to do with the voltage and voltage only. So we're going to step down by 10, so this becomes 5 volts. The power in the secondary coil must be the same as the power in the primary coil. So we know that's 250 because the amount of wattage there must be the same wattage there. And as a result, if 5 times watt would equal 250, then that must be 50 amps. So we haven't created or destroyed energy. The energy of the primary coil must equal the energy of the secondary coil. So that's a step-down transformer. The other option we've got is a step-up transformer. The step-up transformer happens when the primary coil's number is less than the secondary coil's number. So here, let's have our primary coil. Once again, we'll make this 5 volts this time, and let's put it, we'll put 20 amps in there, okay? And we'll have maybe 5, I've got too many 5s there, let's make a different number. Make that 4 windings on that coil. And here in the secondary coil, we've got, let's make it 20 windings, okay? So the primary coil has less windings than the secondary coil. In this case, it is a step up. So last time was a step down. The step up means it steps up voltage. Remember, step up and step down, the two names of these transformers, and they refer to the voltage. So let's now do our NVIP, so VIP, okay, and put the P's for primary, and VIP, secondary, and secondary here. And let's fill in all the information that we have. We know that this is 5 volts and this is 20 amps. I've given you that. We wanted to work out what the whole rest of the situation here is. So we know that we can work out this one here because P equals VI again. So that's another 100 watts. Now, what is going to happen to our voltage? Well, the ratio from the primary to the secondary is a times by 5. That means that the voltage will be stepped up by timesing it by 5. In that case, this becomes 25 volts. The wattage of the primary must equal the wattage of the secondary, so that is 100 watts there. And as a result, we can work out this value here because 25 times this value must equal 100. This is 4 amps. The other way of working out this value here was if the voltage is stepped up by 5, then the amperage must be stepped down in its reverse, so it would be a divide by 5. Okay, so we would divide by 5, just going that way, from one to the other, which it is 20 amps divided by 5 is 4 amps. Okay, so that's a way of doing it. Right, so you've got a worksheet that for this question here. Let's have a look at doing the first of the, sorry, I'll go back to the worksheet. The first of the questions, okay. Right, so over here is a diagram of the situation of the two coils. We've got a primary coil and a secondary coil. Okay, this symbol here is saying there's an AC power source attached to the primary, and this is the output voltage. Right, so we're going to, I'll get you to do it in a few more moments, but we're just going to use our little diagram method rather than using any formulas. So I'm going to draw a primary coil and a secondary coil close by. Okay, and it says that it's an ideal transformer, so we are not losing any energy from the primary to the secondary. And we're using our NVIP here, because I can't fit it underneath. And NVIP here. Okay, secondary, all those. Let's fill in the information from the question. Okay. It's got 5 on its primary and it's got 10 on its secondary. So in this case, it is a step-up transformer. And my diagram is not a good one because it makes it look like there's nearly equal in those cases. Okay. We've been told that there's 30 volts AC in the primary. I've got all S's here, they should all be P's, okay, so change those. So we've got 30 here. What would be the voltage in the secondary? Well, it's 5 going to 10, so this is a times by 2 transformer. So the voltage is stepped up by a factor of 2, so that must become 60 volts. Right, we've given a third piece of information. The third piece of information is 2 amps is in the secondary coil. So that's 2 amps there. Can we work out the rest of the values? If you just want to pause and have a go and then come back. Welcome back. I hope you've had a go at trying to fill in the last 3 values. Going over to this second over here, the power in the secondary coil would be 120 watts because you just multiply these two together. If the power in the secondary coil is 120 watts, going backwards, this must be 120 watts here. And we know that 30 times this value here must equal 120 watts, so that must be 4 amps. Okay. So if we're stepping up the voltage by 2, what have we done here? We're stepping down the current by 2. Okay, so notice that the voltage is increased, but as we've gone from here to here, the amperage has halved. Okay, stop the video now and attempt the questions of the sheet 2, 3, and 4, please. I'll catch you in the next video for question 5.